don't have one. There's not a quiz. Is there supposed to be one? Okay. Oh, there's a test in deform today. Okay, that's good to know. Right. I don't want to. What if stuff changes before then with deform?
What, like velocity physics?
Yeah, something like that.
Sorry, you guys, Newton's law doesn't apply.
Just announce F equals MB.
You're gonna have to talk to Derek about this now. They're actually thinking about redoing a lot of the SI units in known constants. You hear this?
Nope.
It's like instead of no, they're getting like a specific known constant. Like instead of a meter being a meter long, it's going to be a constant that never changes regardless of time.
Oh.
You know what I mean? And then the mass is not going to be like 1 kilogram piece of
To match with relativity
yeah,
stuff. Okay, double subscript notation. Listen, shut up for a second. Double subscript notation for force vectors. Okay, so this notation is going to be useful, especially when we're doing linkages. This is the notation we used all the time, the people who took statics from me. So the force FAB, I'm always going to use to mean the force on A by B. And it's sort of a pain that there's not a there's not a universal way of ordering those. I think physics people more often FAB is the force by A on B. Engineering people more often FAB is the force on A by B. But this is how I'm going to use it. You know, when in doubt, you can always just write stuff. A by B or something like that. You know, just you can make your subscript a paragraph long if you want. You know, just. But when I say FAB, I'm going to always mean the force on A by B. Okay, say it with me. On A by B. On A by B. On A by B. Okay. Good.
You're like recite it, and you're the only one saying it. The whole class just keeps their mouth shut.
I knew Peter would do it. I didn't. If I would have started somewhere else, I would have been less confident that it would have spread around the class. Like, look at somebody and they're just. Yeah. And then, by the way, do not use this notation for scalar variables. That seems like sort of just someone else laying down a bunch of rules. But there's a good reason for this. That's from Cool Hand Luke. Movie you should all see. Paul Newman? Yeah, like 60 something, late 60s, I'll bet. But it turns out that if you use this with scalar variables, you can get yourself mixed up with the signs. That's why. So only use this for vector variables. And now the main reason that this is useful is Newton's third law. Newton's third law is the one that says for every action there's an equal and opposite reaction. Yeah, it's a good law. And there's two ways that we'll use this. This is not either one of the ways that we're going to use it. That's a very confusing, so that's like translated to modern English, like Newton's original wording. Us. Oh, was it in Latin? Yeah. Okay, then yes, it's in Principia, yeah. So for us, this comes up two ways. The first one is force vectors. And let's say, well, I'll just say force vectors. And for force vectors, FAB vector is negative FBA. That's why that subscript notation is cool. You know, it's just so nice and concise. There's no way to get that wrong. If you have a contact force between A and B, and you flip which one you're looking at, you flip the sign of the vector, flip the direction of the vector. The other way is for vectors with known directions. So in that case, let's say we have a body A and a body B in contact. And so a free body diagram of A looks like this. And a free body diagram of B looks like this. So the so R is not going to use that double subscript notation, but this is the same variable. So yeah, if you have subscripts on that, then they're the same. So when you switch bodies, switch the arrow and keep the variable the same, or keep the label the same. Okay, so could you find room over here by the force vectors? As a little example, if you have these two bodies connected by a pin joint, that's body A, that's body B, then the free body diagram of A looks like force on A by B, and the free body diagram of B this force would be the force on B by A, so FBA, and that's the negative FAB. Any questions about that?
Can we choose our own direction?
Oh, yeah, so the directions of those axes should be whatever your coordinate system is in that problem. So if you choose a rotated coordinate system, then just draw those at the angle you chose. Because that's supposed to indicate that this is just sort of a shorthand for saying we have an x coordinate that's in one direction and a y coordinate in the other direction.
No, I'm saying if we want the x-axis to be pointing up,
yes,
and the y going right.
Yeah, if you have a different coordinate system, then use the coordinate system you're using in the problem. Okay, so talked about what to do if you have forces with known directions. So we have to. So far, we haven't talked about when you know the force direction. So here are the 3 types, I believe, that we'll have. So 3 forces with known directions. First one is a pushing force. The second is a pulling force, and usually that's going to involve cables, but it doesn't have to. And the third one that I can't think of any problems where we use this in this class, but it's the friction force. Okay, so first is a pushing force. And a pushing force is always perpendicular to the surface of contact. And it's always toward the chosen body. So think about, like, it makes sense that pushing is toward a chosen body if you think about, like, so if your shirt's hanging out and someone pushes on you, you know, which direction does your shirt go? It goes toward, if you're the chosen body, it's going toward you, you know, so. So as an example, if you have 2 objects on rollers, I'll call this one A and this one B, and you have a force of 500 newtons pushing on body B. A free body diagram of A. Well, there'd be a weight force. Call that MAG. And then the ground is pushing on the wheels. So that's this way. I'll call that normal A. And then cart B is pushing on A, so that's a force this way. And I'll call that R. Yeah, that's mg. So the mass of A times G, yeah. And excuse me, I didn't use the double subscript notation because we know the direction. Okay, and this is where you can get into trouble if you treat that scalar like with that double subscript notation. You can get yourself mixed up. I'll show you why in a second. And then free body diagram for B. We have the weight mb times g. We have an upward force, I'll call that normal B. And then the force applied to B by A. Newton's third law says we draw the arrow in the opposite direction and keep the exact same label. Okay, so you would get in what? Yes, thank you. So you'd get into trouble with the subscript notation potentially here if you wrote this as FAB, you know, with the arrow going that way. You drew this arrow going that way and wrote this as FBA, negative FAB, you know, right? So you switch the arrows and you use that subscript rule. And then you end up with a double negative here, which means both of those two forces are going in the same direction and your answer is wrong. So that's why you don't want to use that double subscript notation for scalars. It's because a scalar is always associated with extra information that comes from the direction of the arrow. The second type of force is a pulling contact. Usually involving cables. And the rule for those is the force is along the line of the pull. Maybe it's sort of redundant. But if you're talking about cables, that means parallel to the cable. And away from the chosen body. And again, you can make sense of that just with a shirt or whatever. Like if you pull on something, you can see that force is pulling your shirt away from the body. That's the direction of the force that's applied. So for example, let's say there's a cable there, an object A, another cable connecting it to an object B, and a force of 200 newtons. So the free body diagram of body A. There's the weight, MAG. There's a cable force here that's away from the chosen body. Call that T1. And this cable applies a force away from the body. I'll call that T2. And then a free body diagram of B. That cable's pulling away from B. That's the same cable as in the other free body diagram. So it has the same magnitude, but the force is in a different direction because it's always away from the body. So this is still P2. We have the weight mbg, and then the force of 200. A lot of times, if you're using cables, there's some kind of pulley being used also. So notice with weightless cables and frictionless, massless pulleys, a cable applies the same magnitude tension force along its whole length. The direction can change when there are pulleys, but that's the only thing that changes. And then the last type of force with a known direction is friction. And let me say that what we're talking about here is dry friction, the kind of friction that you talked about in Physics 1. So, by the way, like, when is it reasonable? When can you use the idea of dry friction in a problem? If you're using some kind of like graphite lubrication, or do they call it lubrication?
Lube.
Yeah, graphite lube. They do call it that, right? So graphite. So if you're using something like that, it's okay to use the rules of dry friction. You're just reducing the coefficient of friction. If you're using oil or something, and you're going to get significant effects of the viscosity of the oil, then you have to bring other equations into it that we're not talking about here that come from fluid dynamics. So bearing, well, so just ball bearings, I suppose it depends on the size of the ball bearings. If they're big enough compared to the thing that to the other stuff going on, then you're going to have to deal with the inertial effects of the bearing, just like you would a wheel or something. If they're small and there's not very many of them, then I suppose this would work. I guess actually it depends. So if you're assuming that the answer is I don't know. But I would think that if you're assuming that there's rolling without slipping between the things and the bearings, you probably would just model that. You just model the rolling in there. It wouldn't add so much to the problem. Dry friction would really only come about, I suppose, if the thing is sliding across the ball bearings, which isn't really what you want anyways. Okay, so first, this is parallel to the surface. And second, so I'm going to break this up into, so I guess we're just, what I have here is kinetic friction. So it's parallel to the surface. And it's opposite the chosen body's velocity. And really what matters here is the relative velocity of whatever it's sliding on. It's not like an absolute thing, you know. If you have a thing in a truck that's going 50 miles an hour this way, and a thing in the flatbed is sliding this way on the truck, the 50 miles per hour doesn't matter for the friction. What matters is the direction of the slide. So this is relative to the surface. And we also know the magnitude is the coefficient times the normal force. Yep. Okay, so let's say we have a setup like this. We have one object that's sliding along the floor. Say that's 5 kilograms. And then we have a 2 kilogram object sitting on top of it, sliding relative to it. And these are connected by a pulley. And there's a 50 Newton force pulling that way. And let's say that the coefficient of friction at that surface is 0.2, and the coefficient of friction at that surface is 0.3. And we want to draw free body diagrams. So first, the free body diagram of the 2 kilogram box. We have a weight force of 2 times 9.81, so 19.62. We have a pushing contact applied by the 5 kilogram box, so I'll call that N1. And then which way is the 2 kilogram? Well, let me do the cable tension. Okay, so that's everything except the friction force. So now we have to think about the friction force. Which way is the 2 kilogram box sliding relative to the surface? The right, yep. And so the friction force is going to be to the left. And that's going to be equal to the coefficient between those two surfaces, that's 0.2. Yep, times the normal force that's pushing those two together, so that's N1. And then a free body diagram of the 5 kilogram. We have the weight. 5 times 9.81 is 49.05. We have a normal force. I'll call that N2. That's the pushing force from the ground. We have a cable force this way. It's the same cable as in this case, so T. We have a 50 Newton force this way. We have a pushing force from the 2 kilogram box. That's this direction. You can also just think of that as a Newton's third law thing. Magnitude N1. And now we have to think about the friction forces. The like vector symbol. To make it a fancy note. I just do that to distinguish normal forces from newtons. So whenever I write newtons, it doesn't have that. And normal forces, just sort of in that habit. But I don't care how you do that. Hopefully you can tell from the context whether you're talking about newtons or not. Although, like when I teach physics 1, it always happens that people they'll mix those two up all the time when we talk about friction. Like they'll write coefficient times n, and then they'll think it's coefficient newtons, or they'll write something as 100 newtons and then multiply by the normal force or whatever.
Newton squared.
Yeah. So hopefully you guys are past that.
What's a Newton?
Okay, so friction forces. So first, let's think about the friction between the 5 kilogram and the ground. Which way is the 5 kilogram box sliding relative to the ground? To the left. So the direction of the friction force is to the right. And that has a magnitude of 0.3 times which normal? N2, yep. And then which way is the 5 kilogram box sliding relative to the 2 kilogram box? Still to the left, yep. And so the friction force is in the same direction as the other one, 0.2 times, and this one is N1. And we only draw free body diagrams when we're planning to use Newton's second law or the moment equation. Right now we're still doing particle stuff, so just Newton's second law for now. So this is a planar problem. Newton's second law gives x and y equations, 2 equations. So we have 2 plus 2, 4 equations. And variables, we have 1, 2, 3. That's all, right? 1, 2, 3.
4, 5, 6, 7, 8, 9.
1.
Yeah, there's only 3.
Only 3. Okay. So I guess one of those equations, I'm not sure which one, is just going to be redundant. Oh, no. We have 4 equations. And what's the 4th variable that I'm missing? 4 variables. So the ones here are t, n1, n2, and then when we go to Newton's second law, we'll also have an acceleration. Okay, so let's just do let's solve this one. Okay, solve it. So Newton's second law for the 2 kilogram box. I'll use a coordinate system like this, x and y. For the 2 kilogram box, we have the force P0. We have the weight, 0, negative 19.62. We have the normal force, 0 and 1. We have the friction force, that's negative 0.2 and 1, 0. And all those add up to equal the acceleration. So that's the mass of the box, 2 times, is there anything we know about the acceleration? Do we know anything about its direction? Well, yeah, so we don't know, as far as whether it's going to be accelerating this way or that way, we don't know that. You know, there's things going in both ways, but we know it's going to be parallel to x. So I'm just going to write this as a2, 0, and the signs will come out on their own. And then Newton's second law for the 5 kilogram. We have the force negative 50, 0. We have the weight, so 0, negative 49.05. We have the normal force N2 up and the normal force N1 down. So plus 0 N2 plus 0 negative N1. We have the cable force T0. And then we have the 2 friction forces, 0.3 N2, 0, and 0.2 N1, 0. What do we know about this acceleration? So that's also going to be in the x direction. I'm going to call that A5, 0. Okay, so we have 4 equations here. Let's count the variables again. We have 1, 2, 3, 4, 5. Okay.
I'm just thinking that. What's where were 3 letters?
Yeah, that's true. I couldn't think of any more symbols. Okay, so, but there's one more thing, you know, because that cable is inextensible, we know there's a relationship between those 2 accelerations. And you can always figure out what that is by thinking about what happens when the position. So think about this position, you know, the position of this moving an inch that way. Okay, what happens to this one? It moves an inch the other way. So the fact that the magnitudes of those displacements are the same means the magnitudes of the velocities will be the same, accelerations will be the same. And since they're in opposite directions, we can say that A5 is negative A2. And so you can substitute that in, or you can just use it as a 5th equation. Okay, so how are we going to solve this system? Yeah, the easiest way to do it is in my opinion, the easiest way to do it in your calculator is list out all the variables. So let's call them T, N1, N2, A2, A5, and then I'm going to make, so each one of these is a column. Yeah. So this is the constant. And we're going to express each one of these, and the rows are going to be the different equations. So there's equation 1, 2, 3, 4, 5. And for each one of those equations, we're going to get any constants by themselves on the right side, and we're just going to write down the coefficients for those variables. This is the augmented matrix if you've used reduced row echelon form before. So for equation 1, the coefficient of t is 1. The coefficient of n1 is negative 0.2. The coefficient of a2 is, we have to get that over on the left side of the equation, all the variables on the left and all the constants on the right. So that's going to be negative 2. And everything else is 0. Equation 2, the coefficient for n1 is 1. The constant, once you get it alone on the right side, is positive 19.62. Everything else is 0. Equation 3, the coefficient for t is 1. The coefficient for n1 is 0.2. For n2 is 0.3. For a5, get that on the left side, and that's negative 5. And then the constant is positive 50 when you get that alone on the right side. Then the fourth equation, the coefficient for n1 is negative 1. For n2 is positive 1. The constant is positive 49.05. And then our last equation, the coefficient for a2, when you get it on the left side, is 1. For a5 is 1, and everything else is 0. So if you call that matrix with a size of 5 by 6, call that, say, M in your calculator, and then run reduced row echelon form of M, it'll give you this matrix back. It'll be 1, 0, 0, 0, 0, and then 0, 1, 0, 0, 0. I'm going to fill in the last column last. Then 0, 0, 1, 0, 0. So that 1 just keeps moving along the main diagonal. And I think what you get is, so when you run reduced row echelon form, it'll give you the answers in the order that you listed the variables. So our order is T, N1, N2, A2, A5. So T will give you, I think, 18.49. I think I used all the same stuff. So 18.49. N1 is 68.67. Which one is? All of them are different?
No, the 68.67 is the same, but
Yeah, that's what it should be. Yes, 68.6. Is that what you got? Okay. 10.08. I think I might have changed that force. And then this one is 19.62. And then what did you get for the acceleration? Okay. So this is the tension. N1, N2, A2, A5. Any questions about that? I'll get an assignment posted by this afternoon sometime.
You don't have to.
Oh, come on. You want to learn this. This stuff is cool, isn't it? I mean,